Okay, so previous videos I've talked about work done and then I've talked about kinetic energy. Now I'm going to look at one of those potential energies that we discussed in the first video. And the type of potential energy we're going to talk about is due to gravity, the gravitational potential energy. So if we have this anvil that you see here, were you to lift it up, it's going to have, depending on its position in the gravitational field, it's going to have some energy stored in it. It will definitely have the potential to do some work. So we lift it up over the fuzzy white kitty. The higher you would lift that, the greater the height, the greater its position above a certain reference point is going to have a greater potential energy. It will have the ability to do more work. Also, the more massive that this anvil is, the more likely or the more energy, the more work it will be able to deliver were it to, unfortunately, fall down on said white fluffy kitty. So how would we calculate this quantitatively and get a number rather than just realize, okay, it's bigger when it's higher, the energy, the potential energy is greater when it's higher, and it's also greater when it's more massive? Is it like kinetic energy where it has some velocity squared, or is it a bit more linear than that? So let's take a look at how we calculate that. It turns out that the gravitational potential energy, I'm going to call that E with a G, but some courses, textbooks, and videos will refer to it as PE for potential energy. We'll use it, it's a specific energy of gravity, so potential energy of gravity, gravitational potential energy, again in joules. We'll determine it by using the mass times the acceleration due to gravity at the point location that you are on the Earth. Most of the time we're going to use 9.81 meters per second squared, but really depending on your location that would vary a little bit. Some teachers and courses actually will use 10 as well. It doesn't really matter. So the last part we would work out is the height we would need to know. Now the height, I have a little asterisk on there because it really means not, you have to know what reference point you're measuring it from. So it's really the change in height between the two locations where it will be, either up high and down low, but you wouldn't measure it necessarily from ground level or from sea level. It depends on the question. You'd have to, it's all on where your frame of reference is going to be. So let's take a look at this example. If you're going to drop a 3-kilogram rock onto a tent peg to try and hammer that into the ground. So you have a 3-kilogram rock and you're just going to let it drop down onto it. Calculate the gravitational potential energy, the potential for this thing to do work. Calculate that after you lift it to a height of 68 centimeters or 0.68 meters above the tent peg. So this is not 68 centimeters above the ground. It is, however, above the tent peg. So the reference point goes from the tent peg up to the point, and that's the 68. So the height, this is why I put the asterisk on it. The height was there just to realize that it's just above a certain reference point. So we have been given a mass of 3 kilograms. I put 30, better put a decimal there. 3 kilograms. We know that it was raised through a height of 0.68 meters. And we'll assume, since it gives us no other information, that the acceleration due to gravity is 9.81 meters per second squared. Question's asking for the gravitational potential energy. The gravitational potential energy is just m times g times h. It's just the weight times the height through which it was raised. So our mass of 3 kilograms multiplied by the acceleration of gravity, 9.81 meters per second squared, and the height of 0.68 meters. So if we take a look at what the units would be, you're going to have a kilogram and a meter per second squared, and then you're going to multiply that by meters. So you're going to get 3 kilogram meters squared per second squared. And that, as we saw in other videos, was actually a joule. So now if we grab the calculator, 3 times 9.81 times 0.68, just multiply them straight out, and you get 20.01. So pretty much 20 kilogram meters squared per second squared. So you get 20 joules. So that's the amount of gravitational potential energy that's stored up in that object. So let's take a look at a different question. So if we look at question 27 from our textbook, but you see it here, a framed picture that's to be hung on the wall is lifted vertically through a distance of 2 meters. The mass of the picture was 4.45 kilograms. That's our mass. It was lifted through a distance of 2 meters. So we have m is 4.45. The height is 2.0 meters. Calculate that gravitational potential energy with respect to the ground. So starting from a ground of 0 and then the height of 2 meters, you would work out mass times gravity times height. So 4.45 kilograms times a gravity of 9.81 meters per second squared, and then its height of 2 meters. Multiply that out, so 4.45 times 9.81 and double it gives 87 and a bit of change joules, kilogram meter squared per second squared. So the calculations for gravitational potential energy aren't really complex. It's pretty straightforward. It's only when we start to tie all these together in a conservation question where we're going to need to start thinking about the change in gravitational potential energy. And I look forward to doing that video next.